Welcome to the Frontiers of Physics lecture at the University of Washington. My name is Natalie Paquette, and I'm an assistant professor of physics here at UW. The Frontiers of Physics lecture series brings to the University of Washington and the Seattle community world-class scientists to explain to you the most exciting developments and discoveries in physics. The biannual lecture series started in 2015 and has so far showcased 11 outstanding presentations by top figures in the field, including 5 Nobel laureates. The topics cover a wide range of phenomena, from the early universe to the present, from the galactic scale to the microscopic world of quantum mechanics, from abstract theoretical concepts to the subtleties of otherwise familiar phenomena. The lecture series is only possible through the work of a diverse committee that includes both members of the faculty and our community. Today, it is my great pleasure to introduce 3 distinguished physicists, all 3 from the University of Washington, the 2021 laureates of the Breakthrough Prize in Fundamental Physics, Eric Adelberger, Jens Gundlach, and Blaine Heckel. Quote, for precision fundamental measurements that test our understanding of gravity, probe the nature of dark energy, and establish limits on couplings to dark matter. I will introduce each of our speakers in turn, but want to say first a few words on the import of their tremendous accomplishments. This is my first year as faculty at the University of Washington, and one of the things that drew me to this university was the strength and vibrance of the experimental groups here, including at CENPA, the Center for Experimental Nuclear Physics and Astrophysics, where our laureates work. I am a very head-in-the-clouds theoretical physicist, interested in questions regarding fundamental physics, and as such, I wanted to be at a place not only with great theorists, but where groundbreaking experimental contributions are made, to keep me focused and grounded, to be at a place where great physics gets done and guides our thinking. The experimental contributions by our speakers have given us invaluable constraints on possible scenarios to explain the dark energy and dark matter that constitute 95% of the energy and matter in our universe. Their results are a guiding light for us in a dark universe, keeping us focused and helping us attain clarity and understanding. Without further ado, let me introduce our 3 laureates. Eric Adelberger is a pioneer in developing precision instruments for fundamental physics. He obtained his bachelor's and PhD from Caltech, respectively, in 1960 and 1967. He was then a postdoctoral associate at Stanford University and an assistant professor at Princeton University before being recruited to the University of Washington. His honors are too numerous to mention, but include the Bonner Prize of the American Physical Society for his studies of isospin and paradisymmetry breaking in light nuclei before he turned his attention to gravitational physics, as well as membership in the National Academy of Sciences and, of course, the Breakthrough Prize. Jens Gundlach obtained his PhD from the University of Washington in 1990 and has been at UW ever since. He is a fellow of the American Physical Society and received the Francis M. Pipkin Award of the American Physical Society in addition to the Breakthrough Prize. In addition to his foundational work in experimental gravitational physics, he is an inspiring reminder of the unity of scientific approaches and practice, and also has a research program in biophysics on the nanopore sequencing of DNA. Blaine Heckel obtained his bachelor's and PhD in 1981 from Harvard University. Professor Heckel worked as a postdoctoral fellow at Harvard and as a staff scientist at the Institut La Langevin in Grenoble, France, before coming to the University of Washington in 1983. In addition to the Breakthrough Prize, Professor Heckel has been awarded the Presidential Young Investigator Award, was a Sloan Research Scholar, and is a member of the Washington Academy of Science. Following today's lecture, which will be given by Professor Adelberger, we will have a Q&A with all 3 laureates, hosted by my colleagues, Professors Alvaro Chavarria and Armida Noor Mohammed. Please submit your questions as they occur to you in the YouTube chat box or by email to fpls@uw.edu. You can find the Q&A instructions and information on how to support the University of Washington's Department of Physics in the video description below. And finally, without further ado, it is my great honor to have all 3 laureates as my new colleagues, and please join me in welcoming them this evening as we look forward to the wonderful lecture by Professor Adelberger and the panel discussion with all 3 laureates. So please, Eric.
It's not going into full screen mode. Okay. Good evening. It's my pleasure today to tell you about gravity, which is at this point the biggest open question in fundamental physics. We live, in the point of view of fundamental physics, in the best of times and the worst of times. We have extraordinarily good successes, and we have enormous problems at the same time that lie at the heart of fundamental physics. And I also want to tell you how a small group of gravity experimentalists here at the UW are participating in the search for cracks in our sacred principles. At present, we understand that there are four fundamental interactions in nature. Gravity, which all of you know, lies behind phenomena from falling apples and tides, to the orbits of planets and satellites, to the GPS system, black holes, gravity waves. It's incredibly feeble. Electromagnetism is roughly 10 to the 39 powers of 10 stronger than gravity. Electromagnetism is everywhere. It underlies phenomena from atoms and solid materials to radio and light to transistors and superconductors. The weak interaction deals with radioactivity and neutrinos. It's crucial for the energy generation in stars and the formation of the elements. The strong interaction holds nuclei together, explains nuclear physics, and how quarks lead to an amazing array of particles. At present, we've got really powerful theories that explain these interactions. We call them standard models. Standard because they work very well. Models because we realize they're not the ultimate truth and will have to be improved as we learn more about the universe. The first standard model is the standard model of particles. This involves quantum field theories of the weak, the electromagnetic, and the strong interaction, and it sees them as what we call exchange interactions between point particles. If you have one particle here affecting another particle over there, the way it happens is that it shoots across what we call a virtual boson that carries, that hooks onto the charge of this particle and hooks onto the charge of the other particle, and that's how something over here affects something over there. Okay? Actually, this diagram is the simplest possible one. If you actually do a calculation in the real world, there are many of these. It's a very elaborate thing, okay? And we have discovered, on the basis of many experiments at accelerators and everywhere, that all the matter in the universe can be, so far, I have to step back, the matter we know about in the universe can be understood in terms of a collection of 12 particles and their antiparticles, and then a collection of 3 or 4, depending how you look at it, of things that go back and forth here. The good news, even though this is a very complicated theory, okay, you can calculate something, what's called the electron magnetic moment, agrees with data to 1 part in a trillion, 1 part in a trillion, okay? It has a framework for unifying all 3 of these interactions, which seem so different, electromagnetism, weak and strong forces. It predicted the Higgs boson, which probably you've heard about. It tells us that the vacuum is not actually empty, but it's filled with virtual particles and antiparticles that are swarming around, okay? And there is no convincing evidence yet for a breakdown, but I've got these 2 asterisks here. I'll cut back to that at the end of the talk, okay? The bad news, it cannot describe gravity, okay? It cannot explain why the universe has much more matter in it than antimatter, which we know it does, okay? In fact, as you just heard in the introduction, it cannot account for 95% of the contents of the universe, okay? Now let me show you how an example of its success, okay? This is a test of what's called the anomalous magnetic moment of the electron. The electron behaves like a little tiny magnet, okay? And these people at Harvard have built a trap made of electric and magnetic fields at a temperature only 1/10 of a degree above absolute zero, where they can trap a single electron inside there and hold it for months while they're busy measuring the frequencies of the electron's complicated orbits inside this trap, okay? And from measuring these complicated frequencies and understanding all the details about it, they conclude that this anomalous moment is this number right here. And the number in parentheses is the uncertainty in the last two digits here, okay? This is phenomenally precise thing, okay? The theory is very complicated, okay? Many of the more complicated versions of the diagram I showed you, but it comes out, and again, it's really quite a phenomenal agreement. It's a major accomplishment. So we're right to be proud. We really understand this, okay? The standard model of gravity is Einstein's classical theory of curved space-time. Einstein tells us that gravity is not a force like Newton taught and as we were taught in beginning physics, okay? Instead, freely falling objects are simply following the shortest paths in curved space-time, okay? And Johnny Wheeler has put this in a very succinct way. Matter tells space-time how to curve, space-time tells matter how to move, okay? This is a very different way of looking at the world from these quantum field theories, okay? The good news, it predicted the deflection of light by the sun correctly, okay? It has something called the equivalence principle, which I will be talking more about. It's baked into it. It's just inherent, okay? It predicted the gravitational slowing of clocks. This is something that's essential for the operation of the GPS system, okay? It predicted black holes, these amazing things, okay? It predicted gravity waves, which you've heard about, gravitational waves. And it predicted that the speed of gravity is equal to the speed of light, and that has recently been checked by LIGO and Virgo, okay? And they agree to a part in 10 to the 15th, okay? Phenomenal, okay? Bad news. If you try to calculate what happens at the center of the black hole, you run into problems. You get infinite curvature. Well, generally, when you come up with infinity in a theory, that's a sign that you're using it past its regime of validity, okay? It doesn't incorporate the uncertainty principle, which was so important in these quantum field theories, okay? It doesn't account for something called inflation. It can't explain why vacuum energy doesn't gravitate. The first standard model says the vacuum is full of these things going on. That has energy in it. It ought to gravitate, because Einstein tells us when Johnny Wheeler says matter, he really means matter/energy, okay? Gravity is driven by matter and energy, okay? And why doesn't that energy gravitate? And finally, obviously, this can't fit into a grand unification scheme where you unify all the four forces in one consistent way of looking at the universe. Let me just show you a couple of precise tests here. The beautiful precise test of Einstein's prediction for the way that mass curves spacetime, that was the first part of Johnny Wheeler's analogy, okay, came when NASA sent a satellite to go around Mars, okay? I mean, Saturn. The satellite is going around Saturn. And people observed before the mission, okay, that at one point a path from the Earth to the satellite, a radio path from the Earth to the satellite, passed very close to the sun. In fact, it passed through the sun and came out on the other side, okay? So this gave people a very wonderful way to see how the mass of the sun was bending or slowing down the light as it passed back and forth, the radio waves between the Earth and the satellite. And this picture shows what they observed. Okay, at this point in the curve, this is time in days now, okay? At this point, the sun was directly between the satellite and the Earth, so they obviously can't take data. And these little dots here are the things they measure, and this curve is what Einstein told you it ought to be, okay? In fact, they could show that the way that matter curves space-time agrees with Einstein to 2 parts in 100,000. It's a beautiful experiment. Okay? Now, I'd like to give you some personal remarks. There are good reasons for experimenters to focus on gravity when you're looking for cracks in the standard model, okay? Disclaimer, the viewpoints expressed here do not necessarily reflect those of the UW Physics Department, the UW itself, or the National Science Foundation, okay? Gravity's standard model doesn't know about the uncertainty principle, and no one has figured out how to put it in, and they've tried hard. But the uncertainty principle expresses a deep truth about reality. And I'm personally convinced that eventually it's going to be involved in our understanding of gravity. Okay? A breakdown of the gravity standard model cannot be accommodated simply by adding a new feature. This happened to the standard model of particles when it was found that neutrinos had masses. The standard model said neutrinos were massless. It was found that they had massless. It could be incorporated into it. Okay? Gravity standard model is different. It's very hard to change it. Okay? It has only one free parameter, and that could be added. And in fact, there's quite a bit of evidence for it. It's called the cosmological constant. Okay? And gravity has already shown us big surprises. Okay? And that's the next 3 slides. And finally, it's fun and can be done by a small university group. Here is a picture from NASA, a brief history of the universe. Okay? So time is running along here. The Big Bang and inflation are happening here. And then for the next 400,000 years, you can't look at what's going on with light or anything, okay? Because there's such a hot bed of roiling charges around in here that light just can't get through. But after 400,000 years, the plus charges combine with the minus charges and they become neutral atoms, okay? And now all of a sudden light can travel freely. And if we look at the light that started out from then to today, okay, it has been stretched out, brought to lower frequencies by the expansion of the universe, okay? And NASA put up a satellite, and later the Europeans, that's very far away from the Earth, okay, that looks at this radiation. It comes from all directions, okay, everywhere, okay? In fact, it's extremely uniform, okay? And almost perfectly uniform, as we will see. And another thing this picture shows you is that it took a long time for things like stars to form, okay? And then, as the universe continued to expand, people thought it was going to slow down because gravity pulls everything together. But for big surprise, it's not true. What's happening now is that the universe is expanding, okay? And that's no explanation for that in the standard model right now. But it's one of the free parameters that you could use, okay? Now let's look at what this satellite saw. Okay, this is a full sky picture of the universe 400,000 years after the Big Bang. It was fantastically smooth because this is the map of the temperatures of this radiation, which is only 2.7 degrees above absolute zero, okay? And the little dots are representing the temperatures in this region. They're tiny, okay? These little dots correspond to a part in 10,000 change in that temperature. So the universe was very uniform at that point. And if you take that data and think about it a lot and do a lot of work, okay, including using the standard models of gravity, you find this remarkable result, which has been hinted at several times, okay? Everything we know about and have experienced directly is in this little 5% piece here, okay? All the rest of it is stuff we really have no idea what it is. We know it's there, but we don't know what it is, okay? Why do we know there's this much dark matter? It's an interesting argument, okay? If there were not this dark matter, we couldn't be here today because gravity wasn't strong enough to survive this hot, roiling thing and begin to condense. Gravity wants to condense things into clumps, into galaxies, and so on. And the only way that worked is that there had to be some particles that weren't disturbed by this roiling sea of radiation that could clump up by gravity, and then that could later on draw in the ordinary matter, okay? And why do we know there's dark energy? Well, it has to account for the expansion of the universe instead of it being slowed down by gravity. Now I want to tell you about the other subject, which is dear to my heart, because it's one of the most precise tests of the gravity standard model. It's called the equivalence principle. It's easy to state, and it's really hard to test, okay? Here's the statement. All objects subject only to gravity will fall with identical accelerations in a uniform gravitational field. That's a nice, clear statement, and it's true. Okay? Testing the statement is a different story. We have very powerful techniques, which I will mention later, okay, for comparing accelerations with incredible precision, okay? But the hooker here is this uniform gravitational field, okay? It's much harder to make a sufficiently uniform gravitational field. In fact, we spent a lot of time working on that, okay? So let's talk about what we mean by non-uniform gravitational fields, or gravity gradients, or tidal forces. These are all different words for the same things. Suppose you had an evacuated box, and you stuck it on the surface of the Earth, and you released 4 little spheres, as shown in this cartoon here, okay? And then you watched them fall, okay? You'd find out that the accelerations, gravitational accelerations of each of these 4 spheres is different, okay? The one closest to the Earth has the highest acceleration because it's closest to the Earth. Gravity falls off like 1 over r squared, okay? This one is farthest from the Earth. It has the least acceleration. These 2 on the side actually are coming together because they're all falling towards the center of the Earth, okay? And now this is a picture for a perfectly spherical Earth. But in the real world, we're not sitting on a perfectly spherical Earth. We're living on an Earth that's got inhomogeneities. There's water, there's lead in the rocks, you know, it's complicated, mountains, okay? And so these gradients are actually much bigger than you would deduce from this, okay? And our precision is so good, okay, that a test region, okay, here, can be considered sufficiently uniform, okay? It has to get smaller and smaller. Because, you know, to see the Earth's tides, you don't see it in your coffee cup, you see it in the oceans, right? So you need to have a very small region, okay? And it's surprising, but the size of this small region that where you know the field, so to speak, is uniform enough, is a cube, you know, with a side length of 40 billionth of an inch, okay? In other words, you have to get really effectively small to have a uniform enough field. Now let's go to the topic of how do you measure tiny acceleration differences, okay? It's done with torsion pendulums. And these have played an important role in fundamental physics ever since 1785, okay? Because they're marvelously sensitive to tiny difference between 2 horizontal forces. And this is the instrument that Coulomb used to discover the Coulomb's law of electricity, okay? So you have here a bar with 2 things on the end hanging from a wire, fine wire, and then he has another sphere here, and he can put charges on this sphere and that sphere, okay? And the interaction between the charges on the 2 spheres can either push them apart or pull them together, depending whether their charges are like or unlike. And he did all this with this simple instrument, okay? But the thing is, make this wire long enough and make it so thin that it's just about to break, okay? Then you have an extremely soft spring for this, okay? Extremely soft. And so that a very tiny force will produce a measurable twist in that bar, okay? Clearly, this has applications to study of gravity. It's so terribly weak, you need something sensitive to see little things, okay? Now, here's the first time that we're going to talk about actually testing the equivalence principle. This is a famous experiment done by a Hungarian Count Eöt-Wash, okay? And he was interested in gravity, but he was interested in it for a pecuniary reason. He was using it to find valuable minerals in the ground, which are typically heavier than the other stuff, okay? In other words, he was looking for gravity gradients that were hints that something valuable was underground, okay? And so he built this very sophisticated instrument, actually. Here's the torsion balance. It's got a wire running down here. Here's the bar. Here is one of his test bodies. And there's the other one, way down here, okay? This was meant to measure gravity gradients, okay? But he was smart enough, and he realized that this technique was so powerful that he could use this instrument, which really wasn't designed to do it. It wasn't optimized for it, okay? It was optimized to find stuff in the ground, okay? But just by applying this, and being a very good, careful experimenter, he was able to show, make a tremendous increase in the precision which we knew that all materials fell with the same acceleration. He showed that all materials that he tried, and he tried a whole bunch, okay, fell with the same acceleration within 5 parts of a billion, okay? But then around 50s and 60s, Bob Dickey at Princeton decided it was too important principle for science to rely on that old experiment, which wasn't, you know, it was kind of not really optimized, okay? So he realized that one of the problems of this, as anybody can realize, is that in order to see an effect here, Eöt-Wash has to look through a telescope at a mirror and see where how the mirror is pointed. And then he turns the apparatus around 180 degrees and he looks to see how the mirror is pointed. And if there's a change in that angle when you reverse you know, this way and that way, that's a sign of a violation of the principle of equivalence, okay? So you have built this very sensitive stuff, and then to make use of it, you have to turn it around 180 degrees. Well, it's obviously not the best way to, you know, measure really tiny things, because you're disturbing this when you turn around. Also, Eöt-Wash was sitting here looking at his telescope, and by this time in his life, he was a fairly corpulent person. So his own gravity gradients had an effect on this, okay? So Dickey said, look, the thing to do is look at things falling towards the sun and not to the Earth, okay? The sun is great because it's very far away. Its gravity field is very uniform by the time it gets to Earth, okay? His apparatus is rotated for free as the Earth rotates every 24 hours, so someone doesn't have to go around and jerk anything. You just sit there and you wait 12 hours and, okay. And he had sophisticated electronics and everything. And he found that all things fell with the same, or at least in this case, it's aluminum and platinum or gold, okay, fell with the same acceleration, you know, with this precision. It was only 280 times more precise than Eöt-Wash. Dickey was surprised, actually. You know, here he's using all this modern technology, great idea, okay, and he expressed concerns about the effects of temperature variations, okay, on the instrument. It was buried in a hole on the Princeton University campus, you know, to make it stable. And the gravity field of Eöt-Wash himself, which I just mentioned to you, okay? And then it was done roughly 10 times better by an experiment in Moscow. And there it sat. People said, look, this thing has been tested. It really works. You know, let's leave it alone. There are better things to do, okay? And along comes this fellow named Fischbach, okay? Goes and looks at the Eöt-Wash experiment, and he analyzes it in a way Eöt-Wash couldn't have, okay? This vertical axis here are the difference of accelerations of the pairs of materials that are listed right here. You know, they're kind of exotic materials, okay? And on this axis is something Eöt-Wash couldn't know about, but it was because they didn't have accurate enough measurements. It was the number of neutrons plus protons per gram of material, okay? And he plotted these up, and he sees this nice straight line here. Okay. And he says, hey, I found evidence for a new quantum force, a fifth force, in addition to gravity, electromagnetism, weak interaction, strong force, okay, whose charge was the number of protons plus neutrons, okay? You remember, quantum particles are interacting with charges, the quantum field's interacting with charges. I don't mean just electrical charge, I mean a generalization of charge, okay? And the force didn't fall off like 1 over r squared, the way gravity and electromagnetism fall off, but it became very weak for separations greater than a range between 30 meters and a kilometer, okay? This behavior could occur, actually, if the exchanged boson, remember the things being shot back and forth between the interacting particles, had a tiny mass. It wasn't massless. If that particle being exchanged is massless, you get a 1 over r potential. But if the particle had a tiny mass, then it would fall off just like this, okay? There was no room for such a boson in the particle standard model, okay, where the bosons are either massless, the photon, or very, very heavy, like the W and Z particles. Okay? And he could explain why Dickey didn't see it. Dickey was looking for something so far away that the force had died off long before it got from the sun to him. Okay? So that's how we got started. Okay? This looked interesting. Actually, I was very skeptical whether it was true, but you know, you couldn't tell it wasn't true. It just didn't smell right. Okay? And so you start thinking about, okay, suppose you want to test it. Okay? This is a picture, a cartoon of the Earth. I've greatly exaggerated its bulge due to, you know, centrifugal force because it's spinning around. Okay? And the Earth's shape on the whole is this oblate object, which where every point on it, the sum of the gravitational field force towards the center of the Earth and the centrifugal force pushing it out, okay, add up, and this surface. So this is, you know, suppose this is water. This is where water would be rest in equilibrium. Okay. Now suppose you were looking for a force that had a range of a kilometer or so, well, or even much greater. This little shaded area, it represents the amount of matter that's within the range of the force. Okay. And you see, it pulls straight down on the pendulum. There's no horizontal force here. And I told you that torsion pendulums measure horizontal forces. The horizon here is a line that's, you know, tangent to this thing. You couldn't see it if you were in the, you know, in the middle of a frozen lake or something. Okay. But the gravity gradients are relatively small here, because the place to make a big effect is go to the, say, the bottom of a big cliff in the North Cascades or something, okay? There, the matter that lies within your range has this shape, and it has a component that can, in the horizontal direction, okay? The trouble is that this also has big gradients in the gravity field, okay? So it's like being a scuba diver, okay? And you're searching for sunken treasure, and you're told that the sunken treasures are in places where there are lots of sharks, okay? So the sharks are these gradients, the treasures is having sensitivity to this stuff. Okay? So this was the humble beginnings of what we're, the Eöt-Wash group, okay? After we heard about the fifth force, Blaine, Hecla, and I decided to test it, and we recruited a brilliant grad student, Chris Stubbs, to make it his thesis project. We didn't have any funding for the work, but we were soon joined by 5 others, postdocs, grad students, including Jens, and undergrads. We'd never done gravitational experiments, which was a good thing, actually, because we approached it with an open mind. Okay? In 1 month, we invented the main features of these Eöt-Wash equivalence principle tests. Here are the main features. We put the torsion balance on a continuously rotating turntable, okay? This gave, you know, a nice sinusoidal signal as the turntable turned around, pointing this way, this way, this way, okay? And we could pick the period. Dickey's period was fixed by the rotation of the Earth. Well, that's actually a terrible frequency if you think about it. Everything varies once a day, okay? The temperature, the electric power line voltage, the vibrations, etc., okay? We can boost this to a period, you know, less than an hour. Well, things are much quieter at that time scale than they are once a day. In fact, the only thing worse than once a day is once a year. Okay? And we had an idea that we want to make it as hard as possible for anything else to tell which of our test bodies are which in the apparatus. So here is Christopher putting 4 test bodies. This is a top view. 2 of them are copper and 2 of them are beryllium. And you probably know that copper is much denser than beryllium. But if you look at these test bodies, they're all the same size. That was deliberate, okay? So that, you know, the little streams of molecules don't act differently on beryllium than they do on titanium, et cetera. Radiation pressure doesn't act differently, okay? Because the copper ones are hollow inside. Okay. Everything is gold-coated. The system for measuring the twist of this is light from a laser coming down, hitting some mirrors. And you can't see the torsion suspension fiber here because unfortunately it's behind this support rod. But even if it were, you couldn't see it. It's so fine, okay? And then we said, where should we go to do this experiment? Go to the cascade, the cliff or whatever. And we rapidly convinced ourselves that the best thing to be is right here in what was then called the nuclear physics lab, because it was carved out of a hillside. There's a deep lake on one side, the hill or main campus is on the other, okay? And it had a little bit of, this structure that you want, but it was in we had a well-equipped laboratory, and that consideration governed everything. And we worked and worked for 11 months. We were really excited about this. I mean, here was a chance to do something new, be clever, everything, okay? And we submitted a paper showing that this force didn't exist. And this is what Fischbach deduced from Eöt-Wash's experiment. And these two little points here, which we have blown up over here, were the results from our experiment. Again, this axis is the fractional difference in parts per billion in the acceleration of things. And this axis corresponds to that quantity, neutrons plus protons per gram, okay? So it didn't exist, okay? But there was a point here, okay? Sometimes something that's wrong actually stimulates your thinking, okay? And here we realized that this technique that we had developed was actually very useful at asking a general question, not this particular fifth force, okay? But could there be other things, okay? And you couldn't say there weren't, okay? That was the key. You couldn't say this is obvious nonsense, it can't be true, okay? In fact, it's an area where nobody had really looked carefully, okay? And there could have been things. And so we set out to a program that we would test both of the standard models at the same time by comparing different things falling with the greatest possible precision in our lab on a rotating torsion balance, okay? And since these days, our sensitivity has improved by a factor of 5,000, okay? That's a big amount. Now let me just tell you a little about reality, okay? You start out thinking that the hardest part is getting sensitive to these really tiny differences of acceleration. But in fact, that's the easier part of it, okay? The hard part is understanding all what we call systematic effects that could give you fake signals, spurious signals. That's tough, okay? And what kind of things can do it? Well, we already talked about gravity gradients, okay? You thought you were testing the equivalence principle, but you weren't because the field wasn't uniform, okay? This is something you can handle rigorously, if the theory is good, but these gradients vary uncontrollably. And the second thing is this turntable has to be awfully good, okay? And our original turntable wasn't that good, but they're getting better and better and better, okay? It has to rotate at a very uniform rate, because if it speeds up and slows down and you're looking at it with a optical system that's speeding up and slowing down, it's going to look to you like the pendulum is doing something funny with respect to the optical system, but actually it was the optical system that was doing something funny compared to the pendulum. Okay. Magnetic impurities can be, Dickey pointed out how tiny a little bit of magnetized material in Eöt-Wash's material could have screwed the whole thing up, okay? You have to use very high purity materials. You have to machine them with great care and so on. And then these thermal effects that Dickey talked about as well, okay? And these are really tricky to understand in detail, okay? The only thing to do, or I should say, or certainly the best thing to do, is to have ultra-stable thermal environment, so you don't have to worry about it. Everything sits at the same temperature. This part of the apparatus is the same temperature as that part, okay? The temperature isn't changing, okay? And for studies of short-distance gravity, I'll talk about below, you have to know the exact geometry of the instrument, which is quite subtle. And you have to control vibrations, and that's a major issue, and I'll mention that. So here's the torsion pendulum of our equivalence principle test, the latest one. This is about the size of my fist. There are 8 test bodies here. Well, that's just designed to make it less sensitive to gravity gradients. It looks very complicated, but in a certain sense, it's almost a sphere, okay, as far as the mass distribution of this thing goes, okay? And there are 4 mirrors for being able to measure the twist of this pendulum in any 4 orientations of it, okay? The fiber, suspension fiber, you can't see in this photo because it's so skinny, okay? It's a very symmetrical design. You look at this and you can't tell which test body is which, okay? And it's surrounded by electrical and magnetic shielding. The temperature is controlled to a hundredth of a degree. This thing, if you gave it a little twist and let it go, it takes around 800 seconds for it to make one complete oscillation, okay? The quality factor of this oscillator is 6,000. That means if you, say, took that little thing and carefully turned it by 10 degrees or something and let it go, you know, you come by 20 days later, barring no earthquakes or something in between, the thing's still going, okay? And everything's made very precisely. And this is the turntable it hangs from. It's quite a sophisticated thing. This rotates with a 20-minute period, roughly, okay? And by now, we've understood a lot about gravity gradients, okay? The constant rotation rate was obvious from the beginning, but it's also true that the rotation axis of this turntable must correspond to down, the direction of down, okay, at the pendulum center of mass, okay? And it's an air-bearing turntable, and here I show it rests on 3 feet, okay? And these are thermal expansion feet, okay? To the level of our laboratory room and any other room varies during the day and the weather and everything like that. It's constantly moving around, okay? And that is a problem because you can't keep the rotation axis of the turntable aligned with down at the pendulum, okay? And so what this has to do to take into account what happens to the variation of the floor, we call that tilt, okay? It has to expand or contract by about a 10,000th of an inch, okay? And so you just change the temperature of these things very slightly, and very smoothly and gently it adapts, okay? And this shows, on an earlier turntable, what you see when you measure the tilt on a rotating tilt, okay? And the tilt is up and goes here. This is 1/3000th of a degree, and this is the angle of rotation right here. You see this complicated stuff. Some of it is due to the bearing not being that good, okay? And other things you see are changing with time. Changing with time is because the floor tilt is changing, and that's what makes this pattern change. So you can now lock those feet so that they cancel out this thing. And when you do that, it's beautifully stable. Okay. We measure the gradients by replacing our normal pendulum with a special gradiometer pendulum. Okay. There's this complicated structure, but basically it's a way of supporting some little tiny balls, okay? You see some of the balls right here, okay? They fit in well-determined places, okay? And depending on where you put those balls, you pick out a certain component of the gravity gradient field, okay? So this provides you with a systematic way of canceling the gradients. And this shows what you see when you're measuring the gradients, okay? This is the time, which is, of course, angle of the turntable, proportional. And here is 720 degrees, 2 rotations. And you see this nice signal here, very well resolved, okay? Well, that's the signal of the gravity gradients. And once you know what they are, then you can design something that cancels the gradient. So here's roughly, you know, each of these is about a ton of lead, very carefully shaped and engineered so that it cancels the gravity gradient right here, okay? You cannot make gravity go away, but you can cancel the gradient in a tiny little region. You can't cancel the gradient everywhere, but you can cancel a little tiny region, okay? And this whole thing is mounted on a big turntable so that you can rotate it around this fiber axis for a purpose I will tell you in a minute. So I had a student, Sue, and she did take her equivalence principle data. And then I said, Sue, let's just see if the gravity gradient cancellation is still what it used to be, okay? And it started out, and it was nearly what it should be. But then we kept on taking data, and the canceled gradient got less and less canceled, okay? The reason is, it was early November, the rains came. Rain soaking into the ground changed the gravity gradient here, okay? So you can't stop the weather, but you can tune away the pendulum sensitivity to the gradients by taking those big things, rotating them 180 degrees, so instead of canceling the gradient, they double it, okay? Make it big. Put a big gradient that you understand on the pendulum, and then make the pendulum so that it doesn't respond to that gradient. And we had little screws in here. By very delicate adjustment, these little screws, and I mean delicate, you could cancel out the imperfections in this thing so it didn't feel those gradients, okay? This requires a patient grad student with very good hands, because it's such a delicate little adjustment. Now this plot is maybe a little bit difficult to understand. What's shown here is a frequency analysis of the pendulum twist signal. And on top here is the frequency in terms of the rotation frequency of the turntable. So a signal at the rotation frequency of the turntable would be at 1 here, and there's a little peak there, okay? This big thing is the free oscillation. In other words, give it a little kick and it oscillates all by itself. These other ones that are sharp peaks have to do with something happening at the rotation frequency. These are all coming from imperfections in the turntable, okay? This curve, however, is impressive. That's saying that the noise we see has is characteristic of an object that had 2/3 the energy of a single helium atom at that temperature, at our room temperature, okay? It's really quite amazing. But now here, look, we're seeing something. What's going on? Well, that's the imperfection in the turntable. How do you account for that? Well, simply, once a day, you rotate the apparatus inside the turntable by 180 degrees, okay? That doesn't change anything in the turntable, but it changes the signal from equivalence principle violation. So that allows you to separate those. And this shows the results. And you see a whole bunch of accelerations, towards the Earth, towards the Sun, towards the galaxy, and they're all small. They're about 3 times 10 to the minus 15 meters per second squared, okay? That's equivalent to the change in little g from moving 1 nanometer in the lab, okay? This is really tiny, okay? An object given a steady acceleration of 3 times 10 to the minus 15 meters per second, started 1400 years BC, okay, would now be moving as fast as the minute hand on the end of a clock, okay? I'm now going to change gears entirely, and we're talking about, let's test the inverse square law. Newton says the force between two gravity force diminishes as the square of the distance between them. Einstein agrees with that here, okay? Why do it? Well, there's an interesting length scale you can deduce from the observed density of dark energy. It's about 4 kilovolts of energy per cubic centimeter. It's actually quite a bit, okay? And you can turn that by using Planck's constant and the speed of light into a length, and that length is 85 microns. And for all we know, this number is constant, okay? So maybe that's a significant thing, this number you get here. Significant thing having to do with gravity. We can also search for new phenomena that are associated with the unification of gravity and particle physics. There's only one game in town at the moment that has the hope of doing that. It's called string theory, okay? And it's a really amazing thing that requires 7 extra curled up space dimensions, has hundreds of extra normally massless particles, okay? And all of these could show up as violation of the inverse square law. Finally, you just ought to look because you never know what's there. And this is a picture that shows what these extra dimensions are. They're everywhere. Every spot in space has these extra 7 dimensions, okay? And so they actually can have quite a bit of volume associated with them, even though they're tiny, because they're everywhere, okay? And we heard about a really interesting idea from Arkani Hamed. He noticed that if some of the extra dimensions of string theory were large compared to this incredibly tiny Planck length, it would explain why gravity is so weak, okay? And this cartoon shows his argument, okay? String theory is not only a theory of little strings, it's also a theory of things like surfaces and so on. So let this surface right here actually be our three-dimensional world, okay? And the strings associated with everything but gravity have charges on the end that stick them tightly to the surface. The graviton alone, the particle of gravity according to string theory, quantum theory, couples to everything. It doesn't have any charge, okay? So it's free to travel everywhere. So in this axis here, away from the plane, okay, that's the extra dimensions, the volume of the extra dimensions. And this plane is where we're stuck. We cannot leave this plane, okay? And the explanation why gravity is so weak is that most of the gravitons have gone off into this other place we can't go, okay? And these extra dimensions would have no effect on anything else. You couldn't do any experiment in the lab, you know, with super electron microscopes or anything, because we're all stuck to this brain very, very tightly, okay? And so here's what was known about the inverse square law. How well does it work? And that's where Arkani Hamed said we should go to see the true strength of gravity, down at these short distances. Once you get close to things within that string radius, they change things. Well, that's a really exciting picture, okay? So this shows a comparison of a previous well-known experiment for testing the inverse square law and our experiment. And again, notice how much more symmetrical this apparatus is than that. Notice that here we have a continuously rotating attractor underneath the pendulum, okay? And there are a whole bunch of holes in here, in the attractor and in the pendulum itself. If there hadn't been any holes in the pendulum, and there hadn't been any holes in the rotating attractor, as the attractor rotated, all the gravity do is keep on pulling down, same as always, nothing changes, okay? But because of these holes, gravity has a chance to pull sideways, okay? It wants the holes to line up, which is the same as saying that wants the mass to line up, okay? And so gravity, as you turn this thing very carefully and slowly, there are two ranks of 21 holes evenly spaced around here. You will expect gravity will tug it one way or the other 21 times for every rotation, okay? That's a really sweet idea, okay? I said these experiments are challenging. The reason is the force is very weak. To see things happening at short distances, you obviously have to use little objects, okay? It's very tricky to align these things. I mean, we have, few centimeter size objects hanging from roughly a meter long fiber, and you're trying to line things up at the micron, millionth of a meter level. It's tough, okay? The unshielded backgrounds are enormous. We need to have a conducting foil between the source and the pendulum, okay? And it has to be rigid. And then there's this thing that you don't know about and you're lucky. It's called the patch effect. If you get very close, even to a very good conductor, very clean, no dirt on it, if it's made of crystalline material, the little crystalline, if they're little crystals that are micro-oriented, okay, the electrical potential off of the crystals varies depending which face you're looking at. So there's this very complicated field, electric field near a conductor if you get close, okay? I never learned about this in grad school. Okay. And cleanliness is essential. One little speck of dust getting between those plates, it's over. You can't get as close as you want to get. And this shows Dan Kapner assembling his apparatus. He's got the clean, the bunny suit kind of thing. This shows a picture of Kapner's apparatus. It's a beautiful thing. I think you can recognize that, okay? Again, this sits inside, a gold-coated house and everything. But the symmetry of it and the idea that this attractor is uniformly rotating is very powerful, okay? And our last experiment now is an ultimate version, so to speak, of the geometry of those things. Instead of round holes, okay, we have these spokes. And the pattern is 50% transparent, we say. It's 50% holes and 50% metal, okay? This is a very thin platinum foil, okay? And it has 120 spokes on the inside and 18 spokes on the outside. And this geometry has an analytic solution. You don't have to do a complicated, numerical, horrible thing trying to get this. It's analytic. And the more spokes there are when you go around, the faster the gravitational force dies off as you separate these, okay? And so what we're doing is we're doing two experiments at once. With these 18 holes, we're testing whether something with 18 holes, how it falls off, which is more slow than something with 120 holes around here. So we're measuring, again, a kind of ratio, what happens to one compared to the other. And this also has a nice feature that it's extra sensitive to something new happening at short distances. And this shows a picture. Here is, in this case, it's John Lee's experiment. It was done twice by Ted Cook and then by John Lee. And you see again, we have the three little spheres here that we use to make an absolute calibration of the thing, interacting with three bigger spheres here on the outside, an outside turntable. There's the tightly stretched foil, and the attractor sits underneath, okay? And John Lee here is testing for magnetic systematics by putting up, what's called a Helmholtz-scope, deliberately applying a magnetic field to see what happens. And this shows a simulation that Ted made. Okay, the pendulum is turning around, the attractor is turning around uniformly. It's speeded up by about a factor of 1,000. And the pattern you see in here has to do, it's the combination of the slowly variation, that's from the 18 holes, and the rapid variation, which is from the 120 holes. And the ratio of the slow variation to the rapid ratio variation gives you the real key information you need. He didn't, have this thing twisting back and forth because he's honest. You couldn't see the amount by which it twists back and forth. It's tiny, okay? The angles you may, I should have emphasized, the angles we're measuring, okay, are equivalent to putting, a meter stick on the moon and you looking at it here, how big does that meter stick look to you? That's a tiny angle, okay? That's the kind of angles we're talking about. And the data that Ted and John independently took, this is John's data, okay? What's shown here is the signal that varies 120 times for every rotation of the pendulum. It drops off fast, okay? This is the signal for from the 18 holes, okay, which drops off more slowly. And this is a little, what we call a harmonic, the third harmonic of the 18-hole signal, okay? I'd like you to appreciate just how small these forces we're measuring is. Suppose you could cut a dollar bill into 1 trillion equal-sized pieces. It's impossible, okay? And you could weigh one of those pieces. That's even more impossible, okay? A 1 femtonewton meter, that's this point on the scale, okay, torque, corresponds to a twisting force equal to the weight of 5 of those tiny pieces, okay? It's phenomenally sensitive, okay? That's why these things are interesting. And this shows what we can say is happening at short distances. On this axis is this length scale, okay, which varies here, between a millimeter and 20 microns. Okay, that's the length scale of the range of the interaction. Here, again, on a log scale, is the strength compared to gravity, okay? Here is something that's, gravitational strength, and here is something that's thousands of that. Anything below this region, okay, you're talking about gravity. Anything above this region, you're talking about something stronger than gravity. And these faint lines here are theorists' proposals for things you could see, okay? In fact, we have a whole graveyard of theoretical proposals that we could show you if you ask, okay? And you'll need a mask, because they're dead. We can tell you now that some of these particles that string theory talks about that are inherent in it, okay, must have masses greater than 5.1 millielectron volts, or we would have seen them as a violation of inverse square law. We can say that the largest single extra dimension must have curled up in a radius less than 30 microns. Well, that's about a third the diameter of a hair. Okay, that's amazing that you can get there. Okay, and so this plot here summarizes everything we've done. Okay, and the color for things we've done is shown down here, and these are the inverse square law tests I just showed you. Okay, these are the equivalence principle tests, some of which I told you about, and the other curves are from different kind of experiments. Okay, this is a huge scale here. Okay, this is a huge region we've explored. This is something equal to the strength of gravity, going this way. This is 1 billion times weaker than the strength of gravity. Okay, this is, you know, a third the diameter of your hair in the length scale. This is the distance to the sun. So we've covered a huge region, and we can say that there's nothing in the standard model of gravity that we can detect in this region. There's nothing in the standard model of particle physics you can detect in that region. But there is tantalizing hint of new physics from other experiments which the SENPA is associated. The anomalous magnetic moment of the muon experiment at Fermi led by UW's Professor Herzog, it's basically measuring the same kind of thing, the anomalous magnetic moment, but now instead of the electron, of its 200 times heavier partner called the muon. That makes it 40,000 times more sensitive to new high-energy physics. And here are 2 experiments that measure this quantity, and here's the theory. Now, there's not this beautiful agreement. You know, it's probably a hint of something new. Okay? There's also an experiment called ADMX, led by Professors Rosenberg and Rybka. Okay, it's called axion dark matter experiment. Axions are not in the particle standard model, but they would explain a long-standing puzzle about the standard model, the minuscule value of something called the theta parameter. Okay? Axions also are a leading candidate for dark matter because you want them anyway. You want them to solve this problem. Okay? And this thing looks for the axions converting into a photon in a very big magnetic field. And they have the world's most sensitive radio receiver there. A cell phone on Mars, you know, with an ADMX front end, you know, the electronics of the front end, you could pick up 4 bars of service from the Earth. Now, wild dreams for a distant future, well beyond my event horizon, well beyond, okay? Experiments that explicitly detect the quantum nature of gravity. These will be really hard. But our UW colleagues, Cohen and Kaplan, argue that factors of 10 in the experiment and 3 in the theory of the electron anomalous magnetic moment, okay, could reveal the effect of the graviton, the quantum mechanical partner that carries the gravity force, to the electron's magnetic moment. That would be a phenomenal thing, okay? It's terribly hard, you know. That experiment has been done very well. People are also proposing to cool a pair of tiny particles into the quantum ground states of their traps and look for effects of the gravitational entanglement of the particles. I'd like to close with a observation. A famous European theorist, whose name I have conveniently forgotten, once compared theorists to French farmers who lead pigs to places where they can dig up truffles. Okay, guess who the pigs are in this clever analogy? The experimenters, of course. But one of the pigs pointed out a problem with this clever analogy. The farmer only leads his pigs to places where he knows there are truffles to be found. So I'd like to acknowledge the many undergrads, grad students, postdocs who worked with us in these projects. The work would not have been possible without a help of skilled machinists, excellent shop facilities. And I'd also like to thank the theoreticians here and elsewhere whose clever ideas and interest had a big impact. And of course, to my colleagues Blaine and Jens for a fantastic collaboration. Thank you.
Thank you. Thank you, Eric, for the wonderful lecture. We will now move on to the panel discussion, which will be motivated by questions that people are submitting on the YouTube chat box. So the first question is actually from me. It is to Professor Gundlach. And So we heard from Professor Adelberger about many measurements of zero. Say, we know where you look for effects beyond gravitational theory and you see nothing.
I know, but in our test of the inverse square law, we are actually measuring it. You can think of it measuring big G at a 50 micron scale, if you want.
Okay, so you can correct me because I'm going to the question about big G, which is, you do have a measurement since year 2000 that has only been, its precision has only been matched recently, and that's the measurement of big G. So I want Jens to tell us a bit about the history of that measurement, and Eric, you can comment on how the inverse square law is equivalent or similar.
Okay. I've actually measured, or was involved in the big G experiment in high school. That's really funny. The big G experiment is, you may have seen it in classrooms here or elsewhere. It's this thing that sits in the corner there with these two lead spheres. We had one of those in our high school, actually. And so we asked our teacher, can we measure big G? Can we measure the gravitational constant? We did it, and we got roughly 6.67 times 10 to the minus 10 meters cubed divided by kilogram per second squared. One thing was just wrong. It's the exponent. It's 10 to the minus 11. Our teacher was really happy that we got the thing roughly, the 6.67, but the exponent was wrong. That just tells you how hard these things are and how many effects there are that can fool this measurement. And so around the year 2000 or a little bit before that, there was a big controversy about big G because there were a whole bunch of measurements that were all over the place. There were up to almost a percent away from the accepted value. And so this looked like a situation with a great tension. There were people already postulating all kinds of theories that you could have in order to explain that. And at the same time, I was working on these equivalence principle tests, and Eric just mentioned we measure these gradients there incredibly carefully. And in the gradient measurement, there's, from it, I realized a thing that the biggest uncertainty there was in previous measurements had been with how you measure the mass distribution of the small pendulum that sits inside the big G experiment, the Cavendish experiment that sits in the corner of these classrooms. And what I realized was that there is a beautiful cancellation that one can exploit where the moment of inertia cancels exactly against a gravitational moment that we had understood very well in our gravity gradient measurements. And it totally eliminated that uncertainty. And therefore should make measurements much, much better. When I first mentioned this to a very senior person, he said, Jens, this can't be right, because in the 200 years of gravity, people would have used this concept. It's so nice and beautiful and obvious. And it was obvious in hindsight, of course, like any invention is. And so 2 weeks later, the person came back and said, Jens, you might have a point there. So we tried this thing out, first in a little test apparatus, and then in a dedicated experiment. I got a precision measurement grant from NIST, the National Institute of Standards, and we built a really sophisticated instrument, again, built on turntables, and there were nested turntables and very precisely machined masses. So the machine shop was, again, very, very important in making such an experiment possible. And we measured the gravitational constant. And I have to say, it was one of the more stressful measurements, because here you just didn't know what the actual value is that that was easy to defend. When you make a zero measurement where you basically discover that that effect isn't there, then it's simpler to digest than when you make an experiment where you have to nail down a value in the end to many digits and really commit your career basically on it, that it's right. So it was very stressful, but the nice thing was that the apparatus really had so many things where uncertainties that people had previously experienced in the measurement really totally dropped out. And so our measurement then had a very small uncertainty and is to this date basically the textbook value that you nowadays see in textbooks. The accepted value is mostly determined from our experiment. So that's the accepted value is the value that NIST determines to be the value that you're supposed to use in your calculations. And our value was a little bit higher than previous accepted values, but turns out that all experiments that followed kind of followed our trend, and our also measure that value that we measured. And just recently, a team in China actually repeated our experiment, really part by part and very, very beautifully, and they got exactly the same value. So, one interesting factoid that when you know the gravitational constant very well, then you also know the mass of the Earth very well. So, when we published this value, we also put the mass of the Earth in there, and that made it all over the Boulevard Press. That the Earth had changed mass apparently compared to previous values. Of course, it hadn't changed mass, but it's a more precise and more correct value, hopefully.
Okay, thanks a lot for that answer, Jens. That sounds pretty amazing. Now, it looks like the audience wants to quiz you, because they ask you, this is a question from James Raymond. Can you let me ask this question to Blaine. Can you make an approximation using Einstein's gravity equation that collapses into Newton's inverse square law?
In weak field gravity, the inverse square law is a natural consequences of Einstein's equation.
So the answer is yes?
The answer is yes.
Yes. Okay. Following question. If you put a clock, let's say to Jens, if you put a clock in a centrifuge so the clock experiences 50,000 G, will the clock slow down as if it were sitting on a supermassive planet?
That's a good question. Well, the clock can't tell the difference between gravity and acceleration. That's the equivalence principle. So,
Well, but the clock experiences the Doppler shift also.
yeah, but so it's a question I have to think about. I would think initially, yes, there should be a there should be a clock change, but it's an excellent question.
Thank you. The answer is, I guess it will slow down. Good. So now a question from Shampak Chatterjee for Eric. Is a perfect vacuum possible where no matter, antimatter, or strings exist?
As far as we know, it's impossible to get rid of what's going on in the vacuum, this vacuum energy. It's impossible to get rid of it. It has to be there. And you can think of kind of an analogy, and that is, if you have a hydrogen atom, okay, it has a ground state, okay? That ground state is determined basically by the uncertainty principle. It says if you tried to make the energy lower, okay, you would have to speed up the motion. And so the optimized, the minimum energy you can get is what's the ground state of the hydrogen atom. there's energy in that. It doesn't have zero energy. You can't use it for anything, okay? Because you can't get any more energy out of it. So it's not useful. You're not going to get rich from it. But it's there, and the mystery is, why doesn't that energy, now when we're talking about electromagnetic field, why doesn't that energy gravitate? There's a lot of it. There's a lot of it. In fact, it's called the most famous, the worst prediction of particle physics. Namely, if you take the energy in all the modes of the electric field and add the vacuum energies up for, for this wavelength and that wavelength and that wavelength and that wavelength, all the way up, to a Planck length, okay? All of that ought to gravitate, okay? I mean, I'm just following the rules of quantum mechanics here, okay? That gives you a number which is 120 powers of 10 too big compared to what we observe, okay? There's a real mystery that nobody understands.
I might just add, though, you can change the vacuum energy.
Yes.
So, for example, if you put two conducting plates close together, that excludes certain modes that otherwise had contributed to the vacuum energy, reducing it, and that actually gives rise to what's called the Casimir force between conducting plates.
Okay, so
But
let's
you
go.
won't get rich from it.
Well, let's talk about getting rich. There's here a YouTube question from someone who's a bit concerned about their tax dollars. Why is everything in your lab gold-coated?
It's easy to answer.
The question is for actually Blaine.
Because the electromagnetic background is so much larger than gravitational forces we're trying to measure, you need to reduce the electromagnetic systematic errors, electromagnetic coupling as much as you can. Gold coating makes the equipotential surface better than most, almost, I wouldn't say it's the best, but it's the best we can actually do in our lab to make a surface equipotential and then shield out the electrostatic interaction.
Okay, so there's another question for Jens, and you kind of alluded to this. So your instruments don't look very technologically advanced. So why didn't someone do this before?
They are actually pretty technologically advanced. They might not look like it. I mean, if I were to show you a picture of it, it is actually a pretty sophisticated instrument. The reason why people have shied away from it is simply that these experiments are extremely hard. They're not easy to do. You need to understand a lot of things really, really well because gravity is just so incredibly weak. If you want to measure gravity to high precision and there's some other effect that it has strengths that are similar, then it would very much affect your measurement. So we go through hoops to avoid all kinds of other effects onto these balances. And the reason why people haven't done this is these experiments are extremely, extremely difficult. They take a lot of time to get right, and so they're not easy.
Thank you. So there's a question for Eric. You listed sources of systematic error in the experiments. In your survey, which ones had the largest impact on the accuracy?
Well, it depends what experiment you're talking about. If you're talking about the equivalence principle, okay, there, the departure of flatness of the gravitation, uniformity of the gravitational field was a very important one. Another very important one is the temperature systematic, just because they're so hard to understand. If you deliberately change the temperature of the instrument and look what happens, it's really complicated, okay? And so what we can do is we can deliberately apply a temperature and see how big an effect it has. It has a big effect, okay? And then you say, well, how well do we know that there wasn't some of that in the experiment? That's limited by how well you can actually measure very tiny temperature differences. In fact, that's interestingly the satellite experiment I told you about. Their biggest problem was temperatures.
Okay, thank you. So next question, and this one is from Ben Hansen to Jens. Does the rotation create an electromagnetic field despite it turning slowly?
No, I mean, the electromagnetic field is only created if there are charges that that are being moved. And in our experiments where there are turntables and so on, we go through hoops to avoid charges. And so there's no electromagnetic effect that we're generating with our instrument. There is one thing that we're worried about and that's for example, this motor that drives the turntable around is an electromotor. It has electric fields in there. And we went through hoops again to make those electromagnetic fields so that they don't affect the pendulum. So there's first of all, there's shields. The electric motor is not a regular electric motor that has poles where it goes clunk, clunk, clunk from pole to pole to pole, but it's a copper drag cup where some fast-changing magnetic fields induce an eddy current force that drives the turntable around. So the rotation itself by physics doesn't induce a magnetic field because there's no charges, but then also the technical electromagnetic fields, we are very, very careful with having at very different frequencies and minimized as much as possible. That's a good question.
Thanks. Another question from Alan Callett for Blaine. Is there a point at which the Casimir effect becomes a limitation on the experimental, that is, spatial range of these pendulums?
I wish we could get close enough to actually have a definite experimental proof that it does, but the answer is yes. You get within the sort of micron range. Casimir, the surfaces are too close to stretch a foil in between to try to shield it, and so you would definitely have the Casimir force contributing. Whether you could distinguish that from gravity, that would depend upon geometry and how, I mean, if you knew you were going to encounter it, you might be able to think of ways to distinguish that force from gravity. I mean, that force would be a attractive force between the plates. You could make your gravity be a twisting force, which is what we do with the inverse square law to separate them. But yes, the Casimir force there's no way to shield it at those distances.
Okay, so here's another physics question. This one is from Michael Moroni to Eric. In classical electromagnetism, the magnetic field emerges from the inverse square law and the Lorentz transformation. Is there a gravitational analog of the magnetic field at relativistic velocities?
The answer is yes. It's called gravitomagnetism. There's a very close analogy, and it has to do with now, instead of electrical currents, you have mass currents. And it is indeed, as you said, you can get the magnetic field just from the Lorentz transformation of the Coulomb field. For the same kind of reasons, you get gravitomagnetism from gravitostatics.
Yeah, thank you. Research. So a question from Sam Suder to Jans. This question is basically to learn how to become experimentalist. Where do you learn the skills to build devices as sensitive as you need? That seems almost harder than the experiments themselves, and it's outside of your schooling.
Good question. I think I was always interested in mechanical things. As a kid, I repaired TVs. I actually worked in a TV repair shop, and I repaired cars, and so I love mechanical things. And but then the skills for these experiments, we sort of started teaching them ourselves. It was not an instant process by which we learned everything. I mean, we had to learn that incredible machining tolerances were really important for these experiments. Yeah, so it's a slow adiabatic thing, and you just have to stick with it and stay with it and remain focused on this goal and figure one thing after the other out, and you become an experimentalist.
And learn electronics.
Electronics, yeah. Physics 334 next quarter.
Well, the other thing is, just doing it. Instead of sitting around and worrying, try it out and you'll learn something. That's a very important part of skill as an experimentalist.
So instead of sitting around and be a theorist, just go to the lab and do experiments. That's what you say. All right.
I beg you.
Well, nature is very kind, because if you ask the right question, nature won't lie to you.
That's great.
It's right on. So the physics is what you're testing is actually correct.
Yeah, thank you. So a question for Eric. Is there any point in making these measurements with electrostatic charge to measure deviations from Coulomb's law?
There used to be a point, clearly, okay? But now we can test the quantum mechanical version of Coulomb's law, at accelerators. We have particles called electrons, which you know about. We have the partner of the electron, the muon, and you can collide two electrons. It turns into a virtual photon and turns into two muons, okay? That relies on the theory that you would use for Coulomb's law, okay? And you get to very tiny distances that way. You never could get there directly. But it's been tested because the theory works, okay? In other words, if you measure the probability that E plus electron and positron turn into a positive and negative muon, at energy of 50 GeV or something like that, that corresponds to an extremely tiny difference. So my taste is it's unlikely you're going to learn anything from actually trying to measure it with, macroscopic objects, because it works so well in these accelerator experiments.
We have another question from Brian to Blaine. Would these results put bound on dark matter or dark energy forces?
Could you repeat it a little bit louder?
Would these results put any bounds on dark matter or dark energy forces?
It certainly puts limits on dark matter. So we compared the acceleration of different objects towards the center of the galaxy. Between us and the center of the galaxy, our acceleration is 30% larger than what's accounted for by the normal matter. So 30% of the acceleration towards the center of the galaxy, our acceleration, is due to dark matter. And so by comparing the rate at which different objects fall towards the center of the galaxy, we are seeing, is there a dark component to gravity? Does dark matter couple differently to different materials? And sort of to a part in 10 to the fifth is our sensitivity. We show that dark matter gravitates just like ordinary matter, that there's no additional dark force in addition to the gravitational interaction of dark matter. Dark energy, I don't think we actually say anything definite.
It's very hard to think of a laboratory experiment that can tell you anything about dark energy. I've thought about it a lot. Christopher Stubbs thought about it a lot. A lot of people thought about it. It would be great if you could do it, but no one has come up with a way of testing it. It's too bad. And if you can think of a way, boy, try it.
So a question from Horizon to Eric. Can you speak about matter-antimatter equivalence principle test?
Yes. If matter and antimatter fall differently, okay, that would mean there is something that couples to baryons, for example, okay? We would see that in our experiments because let's consider a hydrogen atom falling and an anti-hydrogen atom falling, okay? The difference in the charge of those is a factor of 2, let's say, okay? The materials we use in our pendulums, the difference in this same thing, okay, is a few parts in 10 to the third, okay? We can compare, for instance, when we compare beryllium and aluminum, we think of it, both beryllium and aluminum can be made up of a certain number of hydrogen atoms plus a certain number of neutrons, okay? And they're just, and then they're bound together with some binding energy. So we can think of what we're doing, by the way we analyze it, that we are checking, do neutrons fall the same as hydrogen, for example, okay? And so we could also, you know, so we can say that it's extremely unlikely that antimatter falls up, okay? That's generally the thing that people talk about. Suppose antimatter fell up. Well, I can tell you that's a ridiculous idea, okay? Because think of the photon, okay? The photon is equal amounts of matter and antimatter. It has no matter in it, okay? If antimatter fell up, the photon oughtn't fall. But I showed you that experiment with Cassini and Saturn and so on. The photons were falling, okay? Even more obvious, we know in our modern, standard model of strong interactions that the mass of a proton or neutron is, 99% in the gluon fields, not in the quarks masses, but in the gluon fields that are holding them together. Those gluon fields are equal amounts of matter and antimatter. Therefore, a neutron ought to fall more slowly than an electron, okay? Well, these are just not credible ideas. You cannot be intellectually consistent and say antimatter ought to fall up, okay, and say that the standard model works. I mean, the quantum field notions work.
Okay. We have a question also about sort of speculations to Jens. So as the future generation of these experiments get more precise, you might potentially find deviations from the standard models. To your opinion, what are the most likely sources of possible deviations, and which ones you personally would find most intriguing and interesting?
That's again a really good question. Certainly, if there are new fields that directly fit or can be molded into a scenario that connects gravity with the standard model, those would certainly be the most interesting ones. And there are certain candidates. String theory has diatoms and moduli, certain particles that are there that would mediate an equivalence principle violating interaction. And so finding those would be really, really interesting and are really interesting candidates to look for.
Okay, sounds interesting. Question from Reed Thompson to Blaine. Can you quantify the tolerances you needed when machining parts for the experiment? Okay, I go louder. Could you quantify the tolerances you needed when machining parts for the experiment? Was it past the point where machining to such small tolerances cost more than the gold coating? They like the gold coating.
Now there's a practical-minded person.
Yeah.
It depends on the component, what tolerance you need, but probably the highest tolerance is required on the pendulum themselves. And I mean, you can't specify more than a tenth of a mil typically, because that's the typical precision of any machine. But we certainly tell the machinists to do as well as they can. And then by symmetry and little tweaking screws allow us to compensate for any imperfections that may have arisen from imperfect machining. Yeah.
Yeah, that makes sense. Stan Curtis asks Eric, were any of your concerns was about when they started building the light rail? Were you concerned about your experiments?
Yes, because the light rail, of course, comes pretty close to the campus. Yeah. And I mentioned that we're very sensitive to vibrations. Yes, indeed. In fact, you know, we may have to, if we want to make substantial improvements, it's possible we'll have to just go someplace else that's quieter.
But did it impact the experiments?
Yes, what it does, in particular, it's these inverse square law at very short distances, because they shake things around. And you've got things very, very close, and something shakes, you know, sometimes they touch. So it has a big, it's really the real limitation on these tests of the inverse square law at short distances are the vibrations.
Okay.
If we didn't have them, we could do a lot better.
So you might end up moving to the Cascades.
Well, no, maybe to LIGO or someplace.
So we have a question from Holler Lake Community Club. They asked Blaine about the clock again. So about the clock in a centrifuge, isn't a subatomic particle in a synchrotron basically that? So is a subatomic particle in a synchrotron basically a clock in a centrifuge? Physics question.
Yeah.
I can tell you, it is, and it slows down. And for instance, we know muons in a storage ring are circling around, okay? Their lifetime is lengthened by the fact that they're in this strong centrifugal force, okay? And the muon, or you know, many examples, particles can live 1,000 times longer than their natural lifetime if they're in an accelerator.
So we have a question from Noah. Is there a theoretical rationale for using 18 and 120-fold symmetries on the rotating attractors? Is there a practical limitation? Also, please give my love to the folks in the nanopore group. So I think, Jens, you're supposed to answer this.
Oh, interesting. Okay, can you repeat the question about the...
So is there a theoretical rationale for using 18 and 120-fold symmetries on the rotating attractors?
So it's not a it's not a direct rationale other than that you want to produce a signal that is at a very different frequency. So the 120 times per revolution signal is at a much higher frequency than the 18 per revolution signal. And so you can tell these things apart in where they occur in frequency very precisely, and then you can form these ratios. But otherwise, you know, ideally you want to go to even larger numbers of fringes, because that allows you to test at even shorter ranges. But there's the only theoretical reason to go to 120, for example, is that you want to have a lot of small sectors that can interact gravitationally, basically.
You just don't want them to be divisible, because then a harmonic of one could affect the other, and so you pick things that are not divisible.
There's a funny
The
story.
18 and the 120 are close, so.
Okay, our first test of the inverse square law, we had 10 holes in the thing, okay? And a reporter asked me, is the 10 holes have anything to do with the 10 dimensions of string theory, okay? I said, no, look, it's really 2 times 5, and 5 is a number you don't find in most things except for automobile wheels, okay? And you want to have 2 because at that point we put 2 little spheres in opposite holes too, okay? The next example we had 21 holes around there in 2 ranks, 42, okay? And 42, you know, is the answer to the question, what's the meaning of life and all of that. Again, it had nothing to do with it. 21 was 3 times 7, and at that point we were using 3 spheres, and okay. And then we had 120 here in the last version. Well, that's the number of powers of 10 by which, you know, the vacuum energy doesn't gravitate, okay? These are all accidents. They're decided by practical considerations of the kind that Jens and Blaine were talking about.
I think now this is the last question, and it's a visionary question. Each of you could answer this one by one. So what's next for the Eöt-Wash group? So Jens, maybe.
Well, so the one thing that we've already done at our group is we understand very, very small effects incredibly well. And LIGO, for example, is affected by a lot of these tiny, tiny effects, just as our experiments are. And so we have done a lot of contributions to LIGO where we go about and understand very subtle effects for them to improve gravitational wave detection. So that's one of the directions. Another direction is we have an experiment in which, you know, it's a complicated scenario to explain, but where a torsion balance can actually possibly detect dark matter directly. A certain type of scenario of dark matter, but that's one of the experiments that we're heavy on at the moment also.
Eric, Blaine, anything to add?
I don't have anything to add to what Jen said.
Okay. With this, we are at the end of another Frontiers in Physics lectures. We would like to thank our guests, the awardees of 2021 Breakthrough Prize in Fundamental Physics, Professor Eric Adelberger, Jens Gundlach, and Blaine Heckel for this inspiring evening. The young audience here at the Walker Ames room, and you who are watching us from all over the world on YouTube. Last but not least, we thank the College of Arts and Sciences at University of Washington, the advanced team, and the UW video crew who facilitated this lecture and helped us along the way. Have a nice evening and hope to see you all in the next Frontiers in Physics lecture by Nobel laureate Dr. Donna Strickland in May 2022. Thank you.